Hello, sixth graders at St. John's for the upcoming 2020 to 2021 school year. The subject of this second installment of your summer work, this video, is going to be a branch of math known as number theory. There are many different types of math or branches of math. There's geometry, arithmetic, algebra, calculus, and more. Number theory concerns whole numbers. 0, 1, 2, 3, 4, 5, 6, and so on. Now, you might think because of that reason, the fact that there are no fractions, no negatives, just whole numbers, you might think that this is an easy topic. And in some ways it is. But it's also an extremely interesting and challenging topic in mathematics. There are some questions in number theory. I'm going to give you one of them during this video. Some very simple questions to pose. But the answer to the question has baffled all mathematicians for centuries. There are things in number theory that mathematicians think are true, but they have not been able to prove. So number theory is interesting, and the main topic of this video is going to be prime numbers. Now, you already know about prime numbers. A lot of this is going to be a review. But before we get to the topic of prime numbers, a couple of vocabulary words from number theory. And it is important that you understand the difference between these two vocabulary words, the word factor and the word multiple. Now, whole numbers have factors and whole numbers have multiples. For any whole number, there is a limited number of factors, a finite. Finite is the opposite of infinite, right? That's what infinite comes from, the opposite of finite. Finite means there's a limited number of them. There are a limited number or finite number of factors of any number, but there are an infinite number of multiples. So let's take an example. Let's take a relatively simple example of the number 24. Now, it is reasonable to list all of the factors of 24. And the way that I've suggested you do this is to think of 1 and 24, write them down, leaving space in the middle, and then work toward the middle. 1 times 24. You see, factors are numbers that multiply to something else. So 1 times 24 is 24. So they are factors. And of course, 2 and 12. I'm working toward the middle. 3 and 8. And I'm almost done. You see, they're pairing off. 1 times 24, 2 times 12, 3 times 8. And finally, 4 times 6. And those are all of the factors of 24. There are a limited number of them. However, the multiples of 24 begin with 24, and the next multiple of 24 is 48. To get the multiples of a number, you start with a number and then you keep adding the number to itself. Or you can also think of it in terms of multiplication, which is why it's called multiples. This is 1 times 24, and then 2 times 24. Whoops. 1 times 24, 2 times 24, and 3 times 24 is 72. And then 4 times 24 is 96. And I'll stop there. But you can clearly see that that list can go on forever. So there are an infinite number of multiples of 24 and a finite number of factors of 24. Let's now consider the whole number 43. Of course, there are an infinite number of multiples of 43. They would begin 43, 86, and then whatever 3 times 43 is, 129, and so on. What about the factors of 43? Let's do what we did before and start with 1 and 43 and work toward the middle. What are some other factors of 43? Well, 2 is not a factor. This is a so-called odd number, so meaning that 2 is not a factor of it. Is 3 a factor of 43? No. If you do 43 divided by 3, you'll get a remainder. There is no whole number you can multiply 3 by to get 43. In fact, there are no other factors of 43. Only 1 times itself. And you know that we call a number like that prime. 43 is a prime number. Here's the definition of a prime number. We exclude 0 and 1 from our conversation of prime numbers. We consider 0 and 1 to be special. We define a prime number as follows. A prime number is a whole number greater than 1 whose only two factors are 1 and itself. Make sure you understand that. I'll repeat it. A prime number is a whole number greater than 1 whose only two factors are 1 and itself. According to the definition I just gave you, 2 is a prime number. It's greater than 1, and the only two factors of 2 are 1 and 2, 1 times 2. 3 is also prime, but of course 4 is not. 4 is not prime because 2 times 2 is 4. There are factors of 4 other than 1 and 4. 5 is prime. The only two factors of 5 are 1 times 5. 6 is not prime. 7 is prime. 8 is not prime. And you may be detecting something here. 2, of course, is even. It's prime because it fits the definition. But we're not going to have any other even numbers that are prime. Why not? Think about it. Any even number, a number that ends in 0, 2, 4, 6, or 8, is going to have 2 as a factor, so therefore it's automatically not prime. Now, 8 is not prime. What about 9? Well, 9 is not prime because 9 can be represented factored as 3 times 3. 11 is the next prime number. 13 is prime. Now I'm going to skip 15. 15 is 3 times 5, so it's not prime. I'm going to put 3 dots here, indicating that there are an infinite number of prime numbers. We're going to talk toward the end of this video about some other interesting aspects of prime numbers. But for now, I will say that there's a proof that there are an infinite number of prime numbers that is very old. It goes back at least to ancient Greece, about 200 to 300 years before Christ. So over 2,000 years, humans have known how to prove that there are an infinite number of primes. The next thing I want to talk about, I'm going to use the number 48 as an example. I want to talk about something known as the fundamental theorem of arithmetic. Now, in math, when math people use the word theorem is similar to the word theory. Theories are parts of science. A scientist develops a theory as to why something is the way it is and then attempts to prove it or maybe disprove it. I'm not sure why in math they're called theorems rather than theories, but they're kind of the same. In science, it may be difficult to absolutely prove a theory, like currently many people in 21st century world believe in something called the theory of evolution, that life on Earth evolved from simpler life forms. To come up with an airtight proof of that might be impossible. But in math, there are such things as airtight proofs. When something is called a theorem, it means that it has been proven to the satisfaction of mathematicians that the proof is valid and sound, that it proceeds step by step in a logical way from simpler assumptions to prove the theorem. The fundamental theorem of arithmetic has been proven. It's a little bit too complex for me to present to you. Most of the time when I teach you math, I'm going to want to say why and explain why something is the way that it is. I hope you remember me doing that many times in 5th grade. But there are certain theorems that are just too complex in their proof to present to 5th graders. But the fundamental theorem of arithmetic is easy to state and understand. And it says this, that for any whole number greater than 1, it starts the same way as the definition of prime number. For any whole number greater than 1, there is a unique prime factorization. Now we have to talk about what prime factorization means. Let's look at the number 48. Now 48 is clearly not prime. 48 has a lot of factors other than 1 times 48. We can represent 48 as the product of only prime numbers. And you might remember this, doing this, as something we call battles in the 5th grade classroom. I had 2 students come up to the board, and I took the same number, and I had each student work out through a process called a factor tree to come up with the prime factorization of the number. And I would intentionally start each student at a different place. I might start one student with 2 times 24, but the other student with 3 times 16. By the way, 3 times 16 is 48. Okay, now they're starting at 2 different factors of 48, but they're going to end up with the same answer. That was the whole point of the so-called battle. It really, like, I hope you realize that they weren't really battles. I wasn't really interested in who would finish first. Speed is sometimes important in math, but it's not the most important thing by any means. So we weren't looking to see who would finish first, but I was kind of pretending that, well, who's going to get the right answer? But I knew they were both going to get the same answer because of the fundamental theorem of arithmetic. Now, this person might continue with the 24, 3 times 8. And see, even here, at this level of 24, there are several choices you could have made to factor that. But it doesn't matter. No matter how you go about with the factor tree, you're going to get the same result. As we're making this factor tree, I have you circle, once you get to a prime number, you circle it. You can't go any further. You could write 1 times 2, but that doesn't get you anywhere. We don't consider 1 when we're talking about whether numbers are prime or not prime. Now the 8, of course, 2 times 4, the 2 is prime, and then the 4 can be 2 times 2. So starting with 2 times 24 and making the choices that I did, ended up with 1, 2, 3, 4 2s and a 3. 4 2s and a 3. We're going to agree to write that this way. 2 to the 4th power times 3. We're going to put the factors in order from least to greatest just because it looks nice. And we're going to abbreviate with exponents. Instead of writing 2 times 2 times 2 times 2, we'll write 2 to the 4th. That's what 2 to the 4th means. And then times the 3 that we also got. And by the way, 2 to the 4th is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. And 16 times 3 is 48, which happens to be what I chose here. Now, if you continue over here, we'll circle the 3. Right? It's prime. 16, well, let's write it as 4 times 4. But neither one of those 4s is prime. So we'll keep going with the factor tree. Factor each of the 4s as 2 times 2. And we get the same result. 1, 2, 3, 4 2s and a 3. So the same result as before. And that is an example of the fundamental theorem of arithmetic in action. No matter how we went about it, the only way we can represent 48 as the product of prime numbers is 2 to the 4th times 3. Now, you might say to me, Mr. Leffel, what about the order of them? Couldn't we say that it's 2 times 3 times 2 times 2 times 2, or 3 times 2 times 2 times 2? Yeah, there are many ways you could rearrange these numbers, but we don't really consider that because then we couldn't say that the prime factorization is unique. So ignoring the fact that we could change the order, this is unique. This is the only way you can represent 48 as the product of only prime numbers. That is known as the fundamental theorem of arithmetic. Preview. Here's a preview. At St. John's, I teach most of the 8th graders a full high school Algebra 1 course. And in that Algebra 1 course, I teach the students that there is something called the fundamental theorem of algebra. And I state that for them. Again, I don't prove it because that's way beyond what an 8th grader or even I could understand. There is a proof, which is why it's called a theorem. Fundamental theorem of algebra will be upcoming for you in the future in 8th or 9th grade. And finally, in K to 12 math, some students reach a branch of mathematics known as calculus in 12th grade. Others might take calculus in college. And there is such a thing as the fundamental theorem of calculus. So you'll have 2 more fundamental theorems to learn in the future. But right now, you know the fundamental theorem of arithmetic. At this point, we might ask, what about a number like 89? What is the prime factorization of 89? Well, I can tell you, and you might want to confirm for yourself, 89 is prime. What you can do is just try the whole numbers beginning with 2. Is 2 a factor? No. Is 3 a factor? No. You can actually skip 4 because if 2 is not a factor of a number, then 4 cannot possibly be. Is 5 a factor of this? No. 7? Again, I'll skip 6 because if 2 and 3 are not a factor of the number, then 6 cannot possibly be. You only actually have to go as high as 10 because, and 10 is not a factor here, because once you go past what's called the square root of 89, then you don't have to go any further. That's a little bit of a sophisticated topic right there for new 6th graders. But anyway, let's just accept that 89 is prime. And by the way, either now or very soon, Google first 100 prime numbers or first 1,000 prime numbers. You'll get a hit right at the top where you'll be able to click and see the first 100 prime numbers. It'll of course begin 2, 3, 5, 7, 11, 13, and so on. And it'll give you the first 100. Or if you want, you can look at the first 1,000. You will see that 89 is on the list of prime numbers. What about 80? So what is the prime factorization of 89? Well, it's 89. We say that the prime factorization of a prime number is itself. Okay. Here's a sort of an interesting thing, a recurring issue for middle school students. Now, you might look at 87 and it might occur to you, well, it seems pretty similar to 89. You might suspect that 87 is prime, but it isn't. It is divisible by 3. 3 is a factor of 87. And I'm not going to go through all the divisibility rules. You should know how to test whether a number has 2 as a factor, 5 as a factor, 10. Those are easy. The divisibility rule for 3, determining whether a number has 3 as a factor, whether the number is divisible by 3. That's the same thing, by the way. If we say that, for example, 3 is a factor of 12, that's true. We could also say 12 is divisible by 3, meaning that when you do 12 divided by 3, there's no remainder. 12 divided by 3 is 4, and there are the 2 factors, 3 times 4. 87 is divisible by 3, and the rule, the test for that is 8 plus 7 is 15, and 15 is clearly divisible by 3, so 87 is. You add the digits, and then if that sum is divisible by 3, then the original number is divisible by 3. And we can test that, of course, by doing 87 divided by 3. And when we do that, we get 29. 87 divided by 3 is 29 with no remainder. So the prime factorization of 87, I could show the factor tree like that. There's only going to be those 2 branches because the prime factorization of 87 is 3 times 29. Now, 3 is clearly prime, and so is 29. You should be able to recognize 29 as a prime number. So that's the prime factorization of 87. 89 is prime. So it really is an issue. You know, it's a big question. Is a number prime or not? That's something that I might get a chance to come back. I think I'm going to hopefully convince you that even though in middle school I'm going to be asking you, is this number prime or not? And I'm going to be asking you to find the prime factorization of certain numbers. But I'm going to make it easy. I'm going to make it reasonable. The ones that I'm going to give you are easy. it is extremely difficult at times to determine whether a number is prime or not. Here's a list of whole numbers, and I'll explain how I chose them in a moment. But 479, 487, 491, 493, 499, 503, and 509. And I will tell you that one of them is not prime. They're all prime except for one. And the question is, which one is not prime? Well, if you do what I suggested in Google, first 100 primes, and you go down the list a bit, and you get into this area, you'll see that one of these numbers is not on the list because it's not prime. But if you didn't do that, if you didn't look it up like that, it would be an extremely difficult question. And here's why. Here comes the answer. I know students always like to see the answer. This is the number that's not prime, 493. Why is it not prime? Because I paused the video a moment ago and I did this on a calculator. Yes, I use calculators. They're a wonderful tool. I did 17 times 29. Notice 17 is obviously prime. When numbers are small, it's sometimes obvious they're prime. And 29 is also prime. 17 times 29 is 493. So 493 is not prime because it's 17 times 29. Imagine if I asked you to find the prime factorization of 493. I won't. Or maybe, maybe for fun, a bonus question or something. It actually wouldn't take that long. You'd have to try, try 2, try 3, try 5, try 7, try 11. You wouldn't have to try 9 because if 3 is not a factor, then 9 can't be. I mentioned that issue before. Eventually, you'd try 17 and you would do 493 divided by 17, realize it's 29 and you'd be done. But imagine if I took, let's say, 499 times 503. Now these are both prime numbers. Imagine multiplying them together. Think about this. I'm not going to actually do it, but if you multiply these two numbers together, you get some big number. That number is not prime because it's 499 times 503. These would be the factors of it. The prime factorization of that big number would be 499 times 503. But imagine if I just gave you that number and asked you for the prime factorization. Nearly impossible. And if you take very big prime numbers, like two prime numbers that are 20 digits long each, let's say, and multiply them together to get a huge number that's not prime because it's that 20-digit prime times a 20-digit prime. As I understand it in a very general way, that is the basis for internet security. When you buy things over the internet and you're giving your credit card number out, sometimes we read about people hack and get people's information, but the information that goes over the internet is what's called encrypted. It's made into a secret code, and the secret code is based upon the fact that if you take two big prime numbers and multiply them together, and then you have that big number that's not prime, nobody knows what the two prime numbers were that multiplied to it. They're a mystery, and they're the secret to the code. They're like the key that unlocks the information. And the best computers in the world, when those two prime numbers are big enough, I think maybe 20 digits each would be enough, I'm not sure. Even the most powerful computers in the world, it would take a really long time to go through all the possibilities to try to determine the two factors of that really big number. Okay, kind of like what I did here with 17 times 29, only much bigger. So that's a little bit of a lesson about how the fact, if you ever ask, when are we ever going to use this? Well, you personally might not get involved in computer coding and encryption over the internet, but some people did, and they learned math, and that made the world better. It created a product that helped the world. So math is useful. Bridges cannot be something older and maybe simpler to understand. You can't build a bridge without math. Engineers and architects need to know math and need to be able to use math to make things. Prime numbers are cool. I like to keep videos under 30 minutes, sometimes under 20 minutes. I see now that we're at 25. So there's going to be a part 2. I will call it number 2. We'll call this one here number 2A, and the next one number 2B, because this is our second installment of the summer math videos and worksheets. And by the way, I think what I'm going to do for the worksheets, and you'll see this in the Google Classroom. When I put it out there in mid-July, planning to record this. I'm recording it now on July 7, but in a week or so, around the middle of July, I'll put this out there, along with some work for you to do. And I think all I'm going to do is ask you to find some prime factorizations. Give you a number like 48 and ask for the prime factorization. And if I give you 43, 43 is prime, so it's its own prime factorization. In other words, the factor trees. Okay, so, and there won't be that many of them, just a little bit of review and practice of that. But math is not just about, when we're in school learning math, it's not just about what's going to be on the test or what the assignment is that the teacher gives. The math is an interesting subject, worthy of learning just for the beauty and wonder of it, just like music or art. And in the next video, I'm going to explore some of just the interesting facts about prime numbers. Even if I don't ask you to really do anything with it, it's still worth your time because it's interesting, it's cool. But before I close this video, as I was talking the last few minutes, I had to sort of stop myself and say a number is not prime. Now, I know a word for that, but I hadn't introduced it, so I'm going to introduce it now. A prime number is defined as a whole number greater than 1 whose only two factors are 1 and itself. But what about the other numbers that are greater than 1? What about the numbers greater than 1 that have factors other than 1 in themselves? Well, we could call them not prime, which is what I did, or we could call them composite. So, for example, 48 and 87, and also that number 493, I think it was, that I came up with earlier. These are all composite numbers. That word composite is an ordinary word in the English language. Composite. It means made up of different things. For example, the noun form of composite is composition. There is a phrase, chemical composition. The chemical composition of water is H2O, 2 atoms of hydrogen, 1 atom of oxygen. Atoms are known as the building blocks of matter. If you put the 2 hydrogens and 1 oxygen together, you have a composite of those elements known as water. The chemical composition of table salt is sodium chloride, sodium and chlorine, Na for sodium, Cl for chlorine. Those 2 types of atoms together as a composite make table salt. Prime numbers are sometimes called the building blocks of the whole numbers. And it has to do, again, with the fundamental theorem of arithmetic. You've got the prime numbers, and then any other numbers like 48 can be built with the prime numbers, just like table salt can be built with sodium and chlorine. The 48 can be built with 2 times 2 times 2 times 2 times 3, 2 to the 4th times 3, as we saw. The 87 was, what, 3 times 29? So the 3 and the 29, which are prime, are the building blocks of the 87. And the 493 was 17 times 29. So those 2 prime numbers are the building blocks of 493. So whole numbers greater than 1 that are not prime are known as composite because primes compose or make them up. Now you could also say that 1 is the building block of all the whole numbers. But you wouldn't do that by multiplication, you would do it by addition. Every whole number can be thought of as a series of 1s added together. The whole number 7 is 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. 7 ones added together. That's really boring and dull. It's like, and imagine how long it would take to write out the composition of a million with addition. 1 plus 1 plus 1. Right. Now, in the field of prime numbers, 1 is not considered prime. Let me explain that right now too. Why do we say that 1 is not a prime number? That's a legitimate question. Because you could say, hey, the only two factors of 1 are 1 times 1. So why isn't it prime? Let's talk about 0 for a minute. Now, 0 may be a little easier to understand. Does 0 have just 2 factors? How many factors does 0 have? Think about it. How many numbers are there, whole numbers, that you can multiply together to get 0? Aren't there an infinite number of them? 0 times 1, 0 times 2, 0 times 3, 0 times 4, anything times 0 is 0. So 0 has an infinite number of factors, so it makes sense to exclude that. But for a long time, people, every time students get exposed to the prime numbers, many of them wonder, why isn't 1 prime? Here's why. I think it's just a matter of mathematicians decided that it's not, so that there could be a fundamental theorem of arithmetic. Remember the fundamental theorem of arithmetic? The only way to express 48 as the product of primes would be 2 to the 4th times 3. What if 1 were prime? What if we considered 1 to be prime? Well, then we could say 48 is 1 times 2 to the 4th times 3. So there's a second prime factorization of 48 if 1 were prime. And in fact, you could say the 48 was 1 times 1 times 2 to the 4th times 3. 1 times 1 times 1 times 1 times 1 times 2 to the 4th times 3. You see, there'd be an infinite number of ways to factor 48 if with prime numbers if 1 were prime. So that's why we exclude it. So, like I said, I'm going to draw it to a close here. There'll be video number 2B coming along, which will explore some other interesting aspects of prime numbers in the general field of math known as number theory. Take care for now. So long, new 6th graders.